Hello everybody to my next session of my Data Science with Mathematica track. Due to recent events, I have decided I'll insert a session about my Corona model, the natural progression after I have talked about MathLink and LibraryLink would be JLink, and I will do that in the next session. But I think due to recent events, I should show my Corona model first. And I predict the end of Corona at the end of March, perhaps even earlier, perhaps actually the third week, if everything goes well in China. So, if you're only interested in my forecast and model about the end of Corona, you will either have to follow my introduction about the logistic regression with a lot of math around that, or you will have to skip this intro and advance to part 2 of this session. Part 2 is where I'm using actual data together with my logistic model. I'm a firm believer in the principle theory first, and that's why I will introduce the theory and the mathematics first before I apply it to the actual data. After all, this session is part of my data science track, and regression, including logistic regression, is absolutely essential for the modern day data scientist. And we will see today how widely applicable the logistic regression is. And here's a picture of this wonderful creature. This is a picture of Corona. All right, let's get started. So in part 1, I start with the derivation of the differential equation of the logistic function, and then we will use it on a few small problems. So, when it comes to the spreading of a contagious disease, it's reasonable to model the rate of increase to be proportional to both the number of people already infected, and those people are called the spreaders, and the number of people who have not yet been exposed. More spreaders and more healthy people means a faster growth of the infection rate, and fewer spreaders and more infected people means a slower growth of the infection rate. And we want to be able to model a certain saturation process, which is a realistic assumption because the growth cannot be infinite. An upper bound is, for example, the total size of the population. You can't infect more than what you have, or you can't eat more food than there is available. You are getting into certain saturation processes. So, using k as a constant rate of proportionality, x of t as the number of infected people and y of t as the number of people who have not yet been exposed, they're sometimes called the susceptible people, we get dx by dt equals k times x times y. And this is our first differential equation, a very simple one. It should be straightforward that it's just the product of these three terms on the right hand side. And if we're introducing one more infected person as a new person of the population, then we get the relationship that x plus y is n plus 1. We have one more person, and that person now is part of x plus y. And we can use that equation to eliminate y in the differential equation above, and in that case we get this form. Notice that it's a factor. In terms of the independent variable, we have x times n minus x. These are the important things to note here. And the obvious side condition here is x of 0 is 1. We have one infected person at time t. And this is a nonlinear first order differential equation, and it's a special case of a more general differential equation, which is called the logistic equation. In this equation we have a and b as constants, and the solution of the logistic equation is widely used in many areas of research and application. In ecology, sociology, epidemics, medicine, even management and marketing. It's widely applicable where we have certain saturation processes going on. A marketing campaign, for example, starts very strong early on, but after a while people either have the product or they get tired. So a marketing campaign cannot grow and get bigger and bigger and bigger. There's certain saturation processes going on in society. So the logistic function is also important for management. So probably the most elementary differential equation we already know it from high school is simply that we're differentiating with respect to t, and on the right hand side we have k times p of t, with k being a positive constant. In that case, p describes an unbounded exponential growth process. And in many applications, this dE provides an unrealistic growth of the population, because usually growth is not infinite. And around 1840, the Belgian mathematician and biologist P.F. Verhulst was modeling the growth of human populations in various countries, and he developed this differential equation. I'll spend a moment on the origin of the name logistic function, because usually people don't know where it comes from. He gave the function name logistic without any justification at all, unfortunately. In a paper he wrote, "Nous donnerons le nom de logistique à la courbe caractérisée par l'équation précédente." And I translate this as, we will give the name logistic to the curve characterized by the previous equation. And back then, in French, the word logistique was associated with military operations, but unfortunately that's not helpful either, because in his paper he studies the growth of populations of various countries. He also presents a lot of statistics about different communities in the United States. So unfortunately we don't know where the name comes from and why he chose it, because in this paper where he introduces the name, he's not talking about any military strategies. So here is his original drawing from the paper, and we can clearly see that we have two curves here, a logarithmic curve and a curve that he calls logistique. And we clearly see that we have an asymptote that will be an upper bound for the saturation process. Okay, and if it interests you, you can find his whole article at this hyperlink from the University of Göttingen. So the simple model here cannot be used when the population is very large, or when there is competition going on for resources like food, water, electricity, fuel, living space, or money. Such factors have an inhibitive effect on the population growth. After all, the growth processes run into overcrowding, there's pollution happening, there are shortages of resources, and so forth. So let's call A larger than 0 the average birth rate, and let's assume that the average death rate is proportional to the population P of t at any time. That's realistic, because people dying are a proportion of the existing population. That means 1 over p times the differential dp over dt is the rate of growth per individual in the population. And we just set this up as an equation. We say that this differential is the average birth rate minus the average death rate, and that comes out to be A minus BP. And multiplying with P, we get the equation that we already saw further up for earlier today. And although Mathematica breaks absolutely no sweat solving it with the function dsolve, let's do it by hand in order to stay sharp and get familiar with apply sides, which is a relatively new function. I believe we got it in version 11, and I think it's extremely useful for symbolic manipulation, and I think you should get familiar with it. So as a first step in this equation here, let's isolate dt, and we do this by flipping the entire equation and then multiplying with dp. So here we have dt on one side. Next, let's set up the right hand side as partial fractions. So p times a minus b p, we set up a minus bp on one denominator and p on the other, right? And then we have to cross multiply. You remember how partial fractions work. And after this, we get this equation after an integration step. As the next step, we should get rid of a in the denominators, and we simply do that by multiplying the entire equation by a, and we simplify. And now a as the denominator is gone, but it's multiplied on the right hand side, which is now a times c plus d. So we also want to get rid of this log on the left side. We want to subtract it from both sides so that we can use a log identity in order to divide. So you remember the logarithm law that log of a minus log of b is log of a divided by b. So when we apply this, we have the log of a fraction on the left side and ac plus at on the right side. So now we want to get rid of the log, so we exponentiate, and we also do that with apply side simply by saying apply the exponential function to both sides and we simplify. But that means now we can solve for p, and here we have pretty much the equation already. So as a next step, I want to remove c from the exponent. You see that we have c here. Let's multiply it out, then it becomes a times c, and bring it in front as a factor. So we can do that, but now it's of course a different constant, right? From the exponential, up here it's in the exponent. When we have it as a factor, it's a different one. But it doesn't matter, I just call it c1 to indicate that it's a different one. It's no longer c, but we can clearly put it in front of it. Okay, and after we've done this, we can now also divide by the exponential function e to the at, which means two terms are losing it, and 1 over this exponential is now e to the minus at. Okay, and with the initial condition p of 0 is p0, which we have to make sure cannot be a over b, then this equation implies that we get a factor c1 of p0 divided by a minus b p0. And if we substitute that, if we use a replacement rule, it follows that we are getting this equation. And this is exactly the same output that the solution of dsolve is that we saw earlier. All right, I want to make a technical point about this function. When the initial condition p0 satisfies that it's between 0 and a over 2b, then the graph of p of t assumes the familiar S-shaped curve that you've probably seen numerous times. It's called a sigmoid curve. And this is how it's usually plotted. Usually the logistic function is only plotted as a sigmoid. And for the standard logistic function, this is also correct. But here in this general case with a and b, we have to take care of the fact that it can also end up in an asymptote. For a divided by 2b being less than p0, less than a over b, it's also sigmoid, but now we have a negative inflection point. And for p0 larger than a over b, the graph shows a pole at this particular point. So we have to be careful. The solution is not always a sigmoid function, but the standard logistic function is, and that is usually the more interesting case. Okay, as a next step, let's apply it to a very simple problem. We'll take one infected student that's returning to an isolated college with 1,000 students. And assuming that the spreading behavior by which the rate of infection is proportional to both the infected and the uninfected students, you are supposed to determine the number of infected students after 6 days, when it's observed that after 4 days we have 50 infected students. So that's like today is day number 5. Yesterday we had 50 infected students. How many do we have tomorrow? And the solution is as follows. If we assume that no student leaves the campus, then we have to solve the following initial value problem. We set up the equation as we had before, right? It's proportional to the number of infected students, but it's also proportional to the number of susceptible students multiplied with a constant factor of proportionality. And we have at time 0, we have 1 infected student. So let's define a to be 1000k and b to be k. Then we can immediately get from the formula above by simple substitution that the behavior follows this law, this formula, 1000k divided by, well, this perhaps a bit more involved denominator. Or we can simplify it, we can divide by k, and then we're getting this much more simplified formula. We know that x of 4 is 50, that's what we have observed, and that means we can solve for it, because this now on day 4 corresponds to 50 people. So what is k? And k comes out to be this number. It's a logarithm divided by 4,000. And that means, after further simplification, that we have this law, this formula for the number of infected students, x of t. We finally have our x of t as a solution with the formula. Up here, we only had it as a differential, we only had it as a growth rate. Now we have solved it, we have x of t on the left hand side. And now it's easy to answer the question how many students are infected after 6 days, because all we need to do is plot the function or create a table. Okay, so the answer to the question is on day 6 it's 276, and we get it for every day. We started with 50 infected people on day 4. The answer to the question is 276 people on day 6, and we can see that after 10 days, well, 47 people haven't been infected yet, but it grows pretty fast. After 10 days, we have about 95%, 96% of our students infected. All right. So in the next section, I want to talk a bit more about growth processes in general, because the logistic function is just one particular case, one particular example of more general growth processes. So let's use some differential equation theory, very simple one, very normal, simple processes, nothing too advanced. So let's look at growth processes from a more general and more mathematical perspective. The logistic equation will just be a special case. So, as we've already seen above, the equation of normal reproduction is when we simply have the right-hand side multiplied with the factor k. So we have change is k times state, or the other way around, state depends on change. Right? This is a very simplified way of thinking it. Change of state depends on state, and state depends on its own change. So if we assume that the size of the biological population, that can be bacteria, fish in a pond, or human beings, is x, and that the rate of growth is proportional to the number of the organisms present, then we get this formula, and it's fairly reasonable for small numbers. This is a realistic assumption when the population is small in comparison to the amount of resources, such as food or whatever it is. And note that the same diffy is also used for negative k, for example radioactive decay. And you may know already from my first session in the financial options track, I make the direction field almost mandatory for pretty much everything. So let's look at the direction field for this. So here we can change k, and I highlight one curve in green in order to show that this is invariant with respect to horizontal translation. So you see that green is always the same shape no matter where I put it horizontally. Okay? And k, we start out with k as a factor of 1, and the growth is faster and steeper the more I increase k. I go to an extreme of 5 here. So you see that the growth happens pretty fast. But you see that the curves are all the same shape, and they're translationally invariant with respect to the horizontal axis. Now, when we have 1, then this is what we started with. This is the normal exponential function. But we can also lower it, and at the point where we are negative, we now have basically negative growth, right? This could be similar to the radioactive decay. We start with a fixed amount first, but then radioactive decay is getting weaker and weaker and weaker in an exponential manner until eventually there's nothing left, right? So we get this behavior for negative k. For 0, of course, there is no growth process. You see that all the lines are parallel to the x-axis. All right, so for positive numbers, we get positive growth. And for negative numbers, we get something that you can really think of like radioactive decay. All right, so of course, the simple reproduction equation can be solved directly. We did that already in high school. We'll skip it here because it's too simple. We just use dsolve, and of course the solution is the exponential function e raised to the power of kt times an initial value. Okay, so that was for the simple case that we use k times t, right? This is called the equation of normal reproduction. That's x prime is k times x. And if we now change it to be k times x squared, this equation is now called the explosion equation. We now assume that the rate of growth is not proportional to the number of individuals, but to the number of pairs of individuals in that population. This is what makes it the explosion equation, and we see in a moment why. That means that for large x, the reproduction happens much faster than in the case of normal reproduction, and for small x, this happens much slower. And this is very realistic in many fields of science, for example in chemistry, where oftentimes the rate of reaction is proportional to the concentration of two reagents. But it also occurs in biology. For example, it's known that whales of a certain species have difficulty finding a mate, and thus the reproductive rate of whales is also subject to the above equation, but for small x. So for explosive processes, you use this differential equation for large numbers. And for modeling certain reproductions of endangered species, you would use the same differential equation, but with small numbers. So let's plot it here. And in this case, again, we are translationally invariant. You can see that the green curve is always the same shape as all the others, no matter to which point I shift it. But we also see that the rise is pretty steep already for k equals 1. And here we actually get poles. Here we actually get asymptotes. There is a certain limit for if you pick one curve, like the red curve or the green curve, there's a certain limit beyond which the curve cannot go to the right. There is a certain limit, like the tangent function, for example. We cannot go beyond the asymptote, even for smaller numbers of k. And if we make k larger, then the growth is even faster, right? It's going up insanely fast for a number like k. But even for lower numbers, relatively smaller numbers like 1, we do get an asymptote. We cannot go beyond that. And as long as we stay positive, even for smaller numbers, we are getting that asymptote. So this cannot go on indefinitely to the right. At 0, of course, we get the parallel lines. There is no growth process. And for negative numbers, we are getting what I would call an implosion, right? The opposite of an explosion is an implosion. So here we have, it's somewhat similar to radioactive decay, but faster, right? The substance, the concentration of the substance will just implode and go down to 0 faster than exponentially fast. Okay, faster than exponentially. Okay, and for some of these numbers, it may not look much different. For this, for example, for k equals 1, this may not look much different, but we definitely have poles or asymptotes. You see that here we have t in the denominator. So if kt x0 is 1, we have a pole, right? We see a pole here whenever this kt x0 is 1. So let's look at this and manipulate a little bit with respect to k and x0, and we see that we have our pole here. It changes with k and it changes with x0, but we see that we definitely have a pole here. This is realistic with an explosion equation. Okay, so if the growth is proportional to the number of pairs in the population, then the size becomes infinitely large in finite time. That's exactly what happens in an explosion. Okay, next I'd like to introduce the logistic curve. The normal reproduction equation x prime equals kx is only applicable if the number of individuals is not too large. As it increases, competition for resources and saturation effects happen. This causes a decrease in the rate of reproduction. Because people are getting fed up with it, or there is not enough resource available, that means the growth cannot happen as fast because there's competition for the resource, or human beings simply are no longer interested in moving to a certain place and moving to a certain area. If you take large cities like San Francisco, Los Angeles, or New York, they're so big that many people say, I'm not gonna move there. I don't want that. So there is a certain saturation that has happened. So a very simple hypothesis is that we can simply replace the constant rate k with an affine function a minus bx. So now as x increases, k goes smaller, k becomes smaller. We thus arrive at a reproduction equation that is a minus b times x times xt. Again, we have growth proportional to the existing population, but it's also proportional to a process that decreases with the increase in x. Right? We can simplify things a little bit now and take the coefficients a and b to be 1, because we can always rescale the x and t axes. And with that we get a much simpler form. We simply use x and 1 minus x. This is equivalent to a minus bx. I just did the substitution, and now we can use 1 minus x instead. And the stream plot looks like this. We have two equilibrium points, 0 and 1, and we can see that the equilibrium point 1 seems to be stable, because if we're coming from above or below, it converges to that number 1. And the equilibrium point 0 is unstable, because if we have a random fluctuation and we go below it, then we're going to minus infinity. Okay, so we can immediately see the process has two equilibrium points, 0 and 1. And between 0 and 1, the process is directed towards 1. For larger than 1, the process is directed towards 1. And for x larger than 0, the process is directed away from 0. Okay? And 1 is a stable fixed point, and 0 is an unstable fixed point. And the fixed points are the zeros of the function. And if we take x times 1 minus x, the right hand side of our diffie, then we have the zeros that are at 0 and 1. Okay? So an easy way to think about stability versus instability: if you throw something in the sink, then it will stay there. But if you put a tennis ball on a melon, it will stay there until it is moved or touched or gets a little bit of a disturbance. Then it will, well, basically roll down. That was it then. That makes it unstable. So in our case, 0 is unstable because as soon as a 0 population is no longer 0, it starts to grow, and 1 is stable because a smaller population will grow towards 1 and a larger population will shrink to 1. That's what makes it stable. So let's try to find the solution of this diffie, and we are getting this equation for the solution. And this looks similar to what we had above, just divide by e to the t, right? Then we have 1 divided by 1 plus another expression where e of t now, where we use e to the minus t somewhere here in the denominator. And if we set initial conditions, x of time 0 is a constant, for example a half, we are getting these two solutions. This is for general x0, and for a half we're getting this curve, we're getting this equation, e to the t divided by 1 plus e to the t. Alright? So for small x, the logistic curve is practically indistinguishable from the exponential curve because 1 minus x is so close to 1. which is what we multiply x with. That means competition for resources has little influence. There's no saturation yet. And let me give you a few examples. One application is the harvest quotas, the harvesting of a crop or a population using quotas. So far, we looked at a free population that evolves only due to its inner laws. Assume now that we harvest part of the population. For example, we harvest fish in a pond or in the ocean. And let's assume for now that the rate of harvesting is a constant, and then this is called a quota. We then arrive at this differential equation. It's the same that we had above, but we're now subtracting a fixed amount from that population. And if we look at that now with a change in C, then we can see that as we increase C, these two fixed points suddenly start converging towards each other until a maximum value of a quarter. We see that we still have an upper fixed point that is stable, a lower fixed point that is unstable, and as C increases all the way up to a point of a quarter, they are getting closer and closer, and at a quarter they have the same value. So if we are coming from above, it's still stable and it stays at 0.5 and a half, but below it goes away from it. Okay? And the moment we go above, like 0.3 for example, then we don't have any stable fixed point anymore. Everything is an evolution to the downside, right? It means we're over harvesting. We are harvesting from the population so fast that it has no chance to regrow. It has no chance to recover. And here we have a somewhat slower over harvesting, somewhat slower extinction of the population. If we make C really big, then it can go pretty fast, right? There is just no fixed point anymore. Everything goes to minus infinity seriously fast. So as the fixed points are the zeros of the equation, this is our fixed point. If we set it to 0, we're getting C equals a quarter. So this is the limit. If we harvest more than a quarter, then we have no more fixed point and it goes down pretty rapidly. All right, so this is a fixed quota, and you absolutely have to be careful. If you are harvesting with a fixed quota, you can overharvest so much that the population goes extinct, slower or faster, sooner or later. All right, so we can immediately see if the harvesting rate is not too large, less than a quarter, they are to equilibrium. The lower one is unstable. And if for any reason overharvesting, the population drops below this number, the population will eventually die out in finite time. The upper one is stable. And the two equilibria converge. This number and this number converge for C going to a quarter. And if the harvesting rate is a quarter, there's only one equilibrium, and that is unstable. And at this point, it is in theory still possible to harvest the population forever. It would work if we are setting this to a quarter again. It would in theory work to have a stable equilibrium here, even at a half, right? It would work. It would always go to the right and not change direction up or down. So in theory, this would be possible as long as the population is always sufficiently large. But any arbitrarily small fluctuation at the equilibrium will cause the inevitable extinction of the population in finite time. And if the quarter is larger than a quarter, there is no equilibrium, and the entire population will die out in finite time. So in theory, a fixed quarter up to a quarter is still permissible, but a maximal quarter of a quarter leads to inevitable instability and should not be admissible. And also as a practical matter, quarters close to a quarter should also be inadmissible because the lower equilibrium rises. So when we look at this plot, then we see pretty quickly that as the upper equilibrium comes down, the lower equilibrium comes up, and at a quarter they meet in the middle. At a half, right? This line here is at a half. But the space between them is getting smaller and smaller. And the difference between the two, I have this here in a second plot, note this minus sign here, is what we can think of as a buffer space. And as we approach a quarter, our buffer space is going down to 0. And you see that the difference here between orange and blue goes down to 0 as we are approaching a quarter. So in real life, there's the danger that random fluctuations may now throw the population below the lower threshold, after which the population perishes. All right? So a better way to harvest quotas is to set them up as relative quotas. That means as a relative fraction of the population. And in this case, we're getting this differential equation. It is similar to what we had before. We have x of t times 1 minus x of t, but we're subtracting p times x of t. That means a proportion of the existing population. This is a much safer way to do that. And if we now look at the stream plot again and we're changing p, then we can see that we can still over harvest with an increasing percentage of the population, and it is still possible to develop this to complete extinction. But we cannot harvest more than what we have, so there's an upper limit of 1 for p. We cannot go beyond 100%, we cannot harvest more than what we have. And then we are reaching this critical point here that we had before, where it's just barely possible to maintain an equilibrium. But this means we have to stay at 100% or below, and 100% is already fairly large. And here as well, the equilibria are coming together. So it would still be safe to use only a small percentage, and we see that the two red lines are coming closer and closer with an increase in the percentage amount of harvesting. But it is still an improvement because of the following. The lower or unstable equilibrium is now 0 and it won't move. It stays fixed there. It's always at 0. And the upper stable equilibrium is now at 1 minus p. So the absolute rate of harvest becomes established at p times upper equilibrium or p times 1 minus p. But this is also the ordinate where the curves 1 minus x times x and p intersect. So if we plot it like this, then we can see the intersection is exactly at that point p. And if we use 0.5, then we are getting the relative harvest rate at a quarter again. So this is a safer way to use the harvesting, and I emphasize again that in this case the lower equilibrium, the unstable equilibrium, does not move up. That's a little bit of a help, right? But we can still over harvest. It's still better to have the unstable equilibrium fixed, at least not moving upwards, and the stable equilibrium at 1 minus p. Okay, so far we have looked at ODEs in one variable. And the next step would be to extend this to the interactions of 2 or more variables, for example, in a predator-prey model. So a simple example would be carp and pike on a pond, or a fox and rabbit population. Right? They're called predator-prey models, and they are special cases of the Lotka-Volterra system of equations. So it works like this: pike eat carp. And if there are only a few pike, then the carp population can grow and recover. But if there are too many carp, then the pike are having a feast and eat all the carp, but that diminishes the carp population again. But if there are no carp left, then the pike die out as well. They don't have any food left, so they starve. So when there are too few carp, it also causes the pike to die, which in turn lets the carp population to regrow again. So with this, we are getting a natural balance between carp and pike, but it is also one that can fluctuate. Here, we're not saying that this will establish an equilibrium that is a constant number. Here we have processes that will end up being periodic. So we are getting non-constant processes for the equilibrium, but they fluctuate. In fact, they end up being periodic. So I want to point out the steady state solutions here are not constant. So the Lotka-Volterra systems are very powerful, but that would be a session on its own in perhaps a differential equations track. Here at this point, we are stopping at just one variable. The moment we go to two or more variables, we can have interactions between them. And this is exactly what would allow us to model predator-prey models as one particular example. There are of course many more. Not all the two variable cases are predator-prey. All right, so let's now look a little bit closer at the logistic growth. Again, using differential equations and a few plots to take home very important points. The general form of the logistic growth is as follows. We have k times f of t as we had before. So proportionality with the, for example, infected population, but also the saturation term where we have 1 minus f of t over L. So that means when we have L as a growth limit, then it makes sense to divide in the saturation term our term f of t by L. This is now a ratio that we're subtracting from 1. So for example, if the initial population is small, then we're subtracting only a very small fraction from 1. So that means we pretty much have the initial growth very strong as we had in the regular growth equation that we had earlier. But when L is large, when f of t is large, then this term approaches 1. And as we're subtracting it from 1, this term approaches 0. That means we're ending this growth process, right? We multiply this with a number that becomes 0 as we increase the saturation. So L is effectively a growth limit. F of t can never exceed it, right? It can be a population size because we can never infect more people than there are. And when it's 1, then we obtain the differential equation that we have above. But L can be any quantity of the same unit as f. They have to be of the same unit because we are dividing them. So when f is small, the reduction of 1 is not significant. So we essentially get k of f of t. And when it's large in comparison with L, then this 1 minus the ratio is small, and this factor of k times f of t makes the overall growth rate small again. All right, then next, let's solve it. We are solving this equation and are getting this expression as a solution. It looks similar to what we had before, except we're now multiplying with L. Before, our maximum was 1, like 100%, and now we can use L units of something, like 1,000 people or 1,000 fish or whatever. Okay, and if next we divide by e to the kt, as we already did before, we're getting a simpler expression, and in the next step we are proving that it's indeed a differential equation. We differentiate that expression with respect to t, and we set it equal to k times the f of t term here times 1 minus that expression divided by L, and we see that these two expressions are the same. This equation here ends up being true. So with the boundary condition f of t0 is L over 2, that means we're setting t0 to be the midpoint, and that also indicates maximum growth. And that point happens to be t0. Because here in this expression, I take the second derivative. You see that I differentiate this expression with respect to t 2 times. We set it to equal to 0, And in terms of real solutions, we're getting t0 as the solution. That means this is the point of maximum growth, because the second derivative is 0, and then the solution is t0. Okay, let's plot this a bit, and let's make the following observations. When we use some real data, such as the point in time is 20 and our growth rate is 20%, and we have a population of 1,000, then we're getting this picture on the left. We have the logistic curve in blue, and we have the first derivative in orange, and you see that the maximum of the orange curve is exactly at 20. That's our t0, right? As we just discovered, this is the maximum growth. And it's here where we have an inflection point on the blue curve, right? From a fast rise, we're changing over to a slower rise. So the inflection point here is where the first derivative has a maximum. And if we standardize these parameters, for example, we set t to be 0, we set the constant factor for the growth rate to be 1, and we set the population to 100%, then we are getting the plot on the right with additional derivatives. And again, my points, note that the inflection point on the blue curve is the maximum of the orange curve, the first derivative. It's a 0 in the second derivative. That's what we did here in the computation. We have a 0 and we set it to 0 in order to compute t as the midpoint. And for the third derivative, note that the zeros of the third derivative correspond to the inflection points on the first derivative. You see that we have an inflection point here exactly where we have a 0 in the third derivative. And coincidentally, well, not really coincidentally, it's also the maximum on the green curve. And the same on the right side. Where we have a 0 in red, we have an inflection in orange and a minimum in green. All right, this is important to notice. This is how this logistic curve behaves, and this is exactly a behavior that I will need in my modeling later on today. So the second example is what's called the standard logistic function, and it looks very simple: 1 over 1 plus e to the minus et. And maybe you've seen this formula already. This formula is used frequently as an activation function in neural network theory. Very often this sigmoid is used as an activation function in classifier systems because it has very sensible properties, predominantly because we're going between 0 and 1 when we're going from minus infinity to 1 and we have a half in the middle. Now the sigmoid is not the only function that has these properties. There are many different activation functions to create neural networks, but this is one of them, and pretty much every introductory class to neural networks uses this function as activation function. All right, I want to point this out. It has very useful properties for many different types of applications, and this is the prototypical activation function when designing neural networks. Okay, next let's look at some critical slopes for the standard logistic function. I've already mentioned it briefly. Let's take the first derivative and let's compute the zeros of the second and the zeros of the third. So here we have our first derivative. The 0 of the second we already figured out, that goes to 0. While here in the standardized case it's 0. Generally it's t0, but we've set t0 to 0. So this 0 here is 0. And if we take the zeros of the third, we're getting these 2 points that correspond to, as I said earlier, the maximum or minimum in the second derivative and the inflection points of the first derivative. And if we now look at them, they have the values of a sixth, a quarter, and a sixth, right? These are the points where the odd derivatives have extrema. So let's plot the whole thing. The zeros in the third derivative give us the inflection points of the first derivative and then also the min-max of the second derivative. And we're seeing that here. I've highlighted that specifically. Let's make note of the fact that these blue points here are the zeros in the red curve. They're the inflection points of the orange curve, and they're minimum, maximum on the green points, right? This is important, and this is what we're going to use in a moment. And we also note that the inflection point of the original logistic function corresponds to the maximum of the first derivative. All right. Next, I point out that with the parameter substitution, the logistic curve becomes the CDF of the logistic distribution function. The maximum slope is a quarter at the midpoint. So if we do a substitution here, T0 becomes mu, and K becomes 1 over sigma, and L becomes 1, we're getting the CDF for the logistic distribution. And at this point, I emphasize that a CDF type of thinking, a cumulative thinking, is quite appropriate here because the numbers that are reported are simply totals. It's the total number of infected people, the total number of deaths, the total number of confirmed cases. So we're not looking at the daily increments. The Chinese data show us total numbers for a given day. Well, a large proportion of the people who are dead today were also dead yesterday. And a large proportion of the people who are infected today were also infected yesterday. So as we're looking at totals, it makes sense to have a CDF type of perspective here for the modeling. And I guess it goes without saying that the CDF usually looks like what we have here as the logistic curve. When we plot the CDF for most distributions, they all assume a shape that looks a little bit like the blue logistic function here, as opposed to the PDF, the density function, where we're looking at things like daily cases, the new cases per day. But given that the data is provided as totals, it makes sense to have some CDF type of mindset here. All right, so in the second part, let's look at the actual data now. We're now ready to apply the logistic function to predict the end of Corona. I start with some thoughts and observations first. The containment of Corona inherently depends on the successful quarantine measures, just period. It is the only way to get a hold of this. Quarantine measures can be very powerful, and I remind you that it was the only way to exterminate rabies in the Western world, as rabies is 100% lethal. And it is particularly powerful and effective in countries where there is tight control over its population. Tight control over its population. And China is doing that very well. And I personally really doubt that other countries could manage quarantine as effectively as China. Next point, if quarantine measures are the main driver of the containment, then I would expect an asymmetric curve, with the decline being steeper than the rise, because measures would be stricter at the end than at the beginning. So we cannot necessarily assume that the solution is going to be entirely symmetric, and that is a good thing. We want the end to be steeper than the beginning. We want measures to be more and more effective. I point out that other people have tried to model Corona with an SIR model, and I point you here to a link to these Australian guys. I'm not too impressed by it. Some of the language is directly plagiarized from Wikipedia. Here's the link to the Wikipedia article. And I also point out that the problem for complicated model with this kind of epidemic is that the susceptible population is not knowable, and it is very large relative to the infectious and recovered populations. And the reason the death rates are relatively low is that a large chunk of the potentially susceptible population probably already has some immunity because of exposure to viruses with similar antigenic capsules. And mind you, I remind you that SARS is similar genetically, and it also started in China, right? And they're both most likely born by rats or by bats. They're very, very similar genetically, and they're both transmitted by rats. So that means the SIR model only works if you can predict the fraction of the exposed population that might be susceptible. But that is only possible with a disease that is well known. And that's why I think this model really has no predictive value. I would not approach this from the perspective of an SIR model. I think this would be the wrong way to do this, because we don't understand corona enough that we can model this susceptible population properly. And again, it will have huge error to model the susceptible population, because a large proportion of the population most likely already has some immunity to similar antigenic capsules. It's important to realize that, because some immunity towards SARS is probably present in the Chinese population. So that's why I'm very skeptical about any SIR models. And in contrast to that, my logistic model is a little bit more raw. It is simpler, but I think it is also more robust. Theoretically, you can fit a logistic curve with 3 data points, as long as these are very accurate. That's important to ensure that the data has to be very good. But the data is becoming more reliable. The Chinese data is becoming more reliable as time progresses. It appears that there are now enough data points beyond the earlier data problems that all the confirmed data can be used. That means the model is getting more and more accurate. And using the logistic model, in the real world, the growth rate K is not constant. Early on, before the epidemic is realized, K may be very high, as no measures have been taken to slow the spread yet. But as the process continues, quarantine measures improve, and there may now even be treatment. So that means with the logistic function, we're getting a blended rate from many factors. And the main assumption is that the epidemic will end with some maximum case and death numbers. So the potential population that could be exposed in China is mind-boggling, but the data do look like case growth rates are declining. And in fact, as I'm going to show you in a few moments, right now we are entering the phase of the most rapid deceleration by the second derivative. And the recent case data are more robust because of larger numbers and accumulated experience with the counting process. The logistic function is neatly designed to calculate L. That's also impossible to model here, but we have all these factors together. So again, we can model the logistic function with just a few data points as long as these are really reliable, but we have that. The data is getting of higher and higher quality as time progresses. And I now explain the rationale of my model. So in terms of a foundation, I point out that there can only be integer cases in the epidemic, and the epidemic should be over when the last case is reported. 0 itself doesn't occur until infinity. That's just part of how these distributions work. And in real life, there should be days with no cases, but then comes up a sporadic case. But for our practical purposes, when it gets down to single digits of new cases per day, the epidemic is essentially over. And mathematically, that means we're looking at the points where the rates change. And I've shown you these plots above. That means where the second and third derivatives cross 0. Those are the points that we're going to be interested in. And the second derivative crosses 0 at the peak of the epidemic, after which the slope is still positive but decelerating. The slope will always be positive, but it is decelerating. And the third derivative crosses 0 at peak acceleration and peak deceleration. And for the actual data, we look at these derivative curves to see what is going on. And then we use those zeros in order to make our prediction for the end of the epidemic. So, all right, let's get our hands dirty. Here is the WHO data. Here's a dashboard and downloads of the data. And the data that I'm using, I'm extracting from situation reports. They're in Chinese, but it's possible to extract the data from these Chinese situation reports directly. I'll point out there are some inconsistencies in the early data. The biggest thing is that in the earlier data, the suspected cases are included with later reported clinical data. And this has now changed, and we'll drop the earlier data later on. But for now, we'll keep it with it. So here's our data. We start January 21st, and the last data point I have is for the 20th of February. So let's create a data set with it. We can study it, we can look at it, we see the data table in a normal data set. And I point out that starting with the 17th, the WHO reports the cases as total cases, no longer as confirmed. So confirmed has become total. All right, this is the data table that we have. And this is the data that we're going to use in our first analysis. I'll be doing a few. So the log plot shows the initial exponential growth, which later approaches a limit consistent with the logistic model. If we look at this, and again note that this is a log plot, I use two log plots, look at the y-axis, we see that we have the exponential growth here, which is consistent with our logistic model. L is the limit, K is the logarithmic growth rate, x0 is the midpoint, and we are getting this logistic function as a template. We're going to use logistic in a moment as a template for the curve fitting. The inflection point, which is the point of maximum growth rate, is at x0. And again, we are setting the second derivative to 0, and we're getting x0 is that very point. Now, let's talk about the total cases. Starting on the 13th of February, China began publishing the confirmed cases plus the total cases in the province Hubei. I think most likely the testing couldn't keep up with the disease there, and the adjustment was made because the deaths needed to match total cases. And going forward, the total cases will be most important in determining when the situation is controlled, as the confirmed cases no doubt underestimate the problem. And the good fit to a logistic growth model suggests that the quarantine is working, and the current data suggests that the epidemic will soon be controlled. So let's look at this. First at the raw data. We're looking at the total data where we are not having missing data, and let's define this properly so that we can do a nonlinear model fit, and we're getting a fitting solution that has K as 0.20, we have L as about 81,000, and the midpoint is about day 18 or day 19. These data now contain cases which earlier were called suspected. Probably the diagnostic criteria had not been fully developed, and I'm adding 5 days because we want to have a proper data range to the upside as well for that. And now let's plot what we have, and we see already visually that we have a very good fit. These are the total cases. There are spots in the middle because data is missing. Let's look at the confidence interval table, and we see that these bounds are really not too far apart. We are talking about a midpoint that is somewhere between day 18 and day 19.3, and we have K between 0.19 and 0.21 on a 95% level. So that means we can now ask at what point is the first derivative 1. Those would be the new cases. And we find that this is at day 65. So if we add this to the beginning, which was January 20, we're coming to an end of the epidemic on March 26. So it's better to use more recent data. The recent data has a little bump, but the recent total data may be the best way to predict the end of the epidemic. And this methodology is likely more consistent than the data at the beginning. So if we are now selecting the days after day 23, and that was the 13th, then let's call them the recent cases, and we do the same model fit with just the recent cases. So we're getting somewhat different parameters. K is now 0.26, L is lower, L is now 79,000, but the midpoint is still similar to what we had before, 19.5. If we are now plotting these bands on a 95% level, we're getting this plot for the recent cases. Let's also look at the residuals, and we see that they're not too far off, less than 420 maybe, a few hundred, no more than just a few hundred, which I think is a fairly good fit. And also the 95% confidence bands show us that our model fits with the data pretty tightly. And it brings me to an end of the epidemic of March 18. Again, we're taking the first derivative of our model and we set it to 1. That means new daily cases would be 1. And that means basically the disease is over. I would accept single digit cases here. I'm setting it to 1. And then I'm adding that number of days to the start, which was January 20, and that brings us to March 18. So the whole thing was over after about 58 days. And we see that the differences of the recent cases predicted by the model and those of the new cases of the model are fairly close. Let's compare the differences with what we have in the first derivative. And we see in the last two rows here that they're not too far off. They're not too far away from each other, generally less than 100 or something like that. Next, I point out that the death data has an error due to the change in counting on February 13. That is because the WHO hasn't spread the increase in deaths on that day over the previous counting. And I think that's highly problematic. They stated that the cases had accumulated, but they didn't try to correct past data. So unfortunately, that means that we're getting a little bit jumpy here. And we see that here in this plot of the differences, that was on the day 24 here. That's 13th of February. And we see that this large jump here is just pretty bad for our data modeling. But I'll show later that it really doesn't change the fact that we have a very robust model with this. So if we are now doing a nonlinear model fit on these death cases with the logistic function as our template, we're getting new parameters here for K, L, and X0. Next, let's plot it. And we're getting this curve. And I think it looks fairly good. It looks fairly nice how our logistic function models the data. So as a list plot of the residuals, we see that the numbers are even smaller. We're now between minus 40 and 40, except for this outlier here. And let's look at the confidence table. So I now want to point out that we're really at the point in time where we have maximum deceleration. So let's take the day, the last day that we have, and let's plot it against the curve. And I am putting a point at the last day in the series, and you will see that the point happens to be pretty much where the orange curve has its minimum. So we're really about at maximum deceleration right now, right? We can see that pretty clearly that the last data point is where our model has a minimum in the first derivative. And that brings me to an end of the epidemic for March 19. So fairly consistent to what I showed earlier. It's now on day 59. Okay, I want to emphasize, although I use the recent cases to predict the end of Corona, And for two reasons: A, the change in accounting, and B, disregarding earlier data errors, I think the confirmed cases up to February 16, you remember we had confirmed cases up to February 16, we didn't have confirmed cases, only totals starting February 17. The confirmed cases up to Feb 16 were already outstanding in confirming the logistic function to be a great model. So let's select all the days that are less than day 28, so that goes up to the 16th. And if we are now trying to build a model, then we are getting a new set of parameters. And when we plot this, we're getting, I think, an absolutely wonderful fit for our model and the data. Let's look at the first derivative. These are the daily new cases. And we see that our model does a great job fitting through that data. With this, I come to an end of the epidemic after 52 days, which happens to be the 13th. Okay, so this is using confirmed cases, but only up to the 16th. Not too far away, and I think this is not as good as the total data that I'm using above, but I think it shows how great the model fits, and the end of the epidemic is not too far away. Here we have the 13th. So even though this data is not as good, we're coming to a similar conclusion. And next, I want to point out, I've done a similar analysis using the data provided as a resource data by Wolfram Research, and I come to similar results. So let's load that in, the Corona data as a resource data. Let's get out the China data. Let's plot it. We're getting this as a time series. And let's extract confirmed cases and deaths. I won't go through all the details. This is methodologically the same as what I've done with the WHO data. So I think I can go over this a bit faster. We get these plots on a 95% level. It looks fairly similar. Let's look at the residuals. Also mostly fairly low numbers, just a few hundred for these residuals. The confidence table, and let's look at the differences again, which is equivalent to the daily new cases, and we see they're coming down. With this, I get an end of the epidemic, again using the first derivative of 1 of March 7. Fairly quick, and I think if this is going to happen, then it's going to be fairly dramatic. So if we're looking at the differences versus the first derivative again, not too far away. If you compare the last two vectors, these differences are not too far away, maybe 100 or less. Okay. So let's continue with the death cases of the data that comes from Wolfram Research or GitHub. And we get these fit parameters, and let's plot them. We're getting this familiar plot shape on a 95 level. And let's look at the residuals. Less than 50 most of the time. Confidence table. And let's again plot the last day in comparison to the minimum in the first derivative, and we see we're about there, right? We are at a point in time that corresponds to maximum deceleration. With that, I get the end of the epidemic as March 21, consistent with what we saw earlier. You remember we had computed the 18th and the 19th with WHO data. This is now the GitHub or Wolfram Research data. Okay, in closing, I'd like to make a couple of final comments. A recent report seemed to be indicating that China would be removing cases that didn't confirm, so that case rates may be going down even more rapidly. I think this should then also be corrected in the GitHub or Wolfram Research data. And according to the WHO, except for the province of Hubei, China is able to count confirmed cases. This would be great. The confirmed cases are a good predictor, not just the death data. If we have a situation where the most recent data only is becoming increasingly more accurate because of count adjustments, then I think we could keep calculating from the most recent 3 points to get a curve and see if the parameters are converging. And I think it would also be worthwhile to conduct such an analysis with the data that excludes Hubei. Overall, I think that would be a great data improvement. I also point out that the WHO data includes Hong Kong under China, whereas the GitHub and the Wolfram Research data have Hong Kong separate. New deaths should be in single digit by the 3rd week of March if these parameters hold. I believe this is what is going to happen. This is what my model predicts. Next, I have to emphasize we only looked at China, but this is only part of the story worldwide. Recently, there were new problems reported in the Chinese Shandong province, and I think that could be as simple as a data error, but also in South Korea and Iran. And the last point, I want to raise the question, can a good model salvage bad data? We have this problem of the bad data point on day 24. So a quick discussion between China and the WHO. I think the coronavirus data leaves many things to be desired. And I think some kind of system that would ensure the correct reporting of suspected, confirmed, lab confirmed and total is hopefully on the post-mortem list for the next epidemic, because it's for sure gonna come. This wasn't the last time. Originally, the WHO started reporting only those cases that were confirmed by laboratory testing. On Feb 13, it became apparent that China could not do laboratory testing in a timely fashion on the increasing number of cases, especially in Hubei. And worse, the WHO was only counting deaths on cases that had laboratory confirmation. I think that's making the problem worse. The WHO then abruptly allowed the counting of clinical cases and added a jump in the death count, but this made the data on laboratory confirmed cases pretty much useless to track the progress of the epidemic, because it became apparent that clinical cases were growing faster than what was possible to confirm with laboratory tests. Due to the death counting problem, the total deaths were abruptly increased without any adjustment to when they actually occurred. They just gave one total number and just threw it out there and added it on top. Well, it doesn't make any sense. We have to provide this data for the days on which it occurred. And about 2 weeks ago, the WHO went a step further and even stopped reporting laboratory confirmed case data separately in China. Next, we have this bad data point problem, as we've seen above. The death data has an error due to the change in counting on the 13th of February, our day 24. The WHO hasn't spread the increase in deaths on the day over previous counting. They just stated that the cases had accumulated, but they didn't try to correct the past data. They just added one total to that current day. They probably have no idea how to do that. So the question now becomes, can the mess be saved by the model? So here's my answer to that question. So let's take the death cases again and let's evaluate our expressions, our data expressions, and let's look at the daily difference in the deaths. And we see here's the data jump. So now it's an interesting question to see if the parameters converge over time. It doesn't seem to be affecting the model much, and again, let's plot it again. We have already seen this data above, but let's just look at it again to convince ourselves that this data problem doesn't give us a problem in the actual fit. And indeed, here's a point that's a little bit to the upside, but it's really not too bad. We have this known data point at day 24, and it's particularly bad because it occurs about the same time as one of the key parameters, x0, which is the point of maximum growth of the epidemic, and having a spike at this point would seem to be a key problem for the credibility of the model. So the confidence table again, and the question becomes, is it still possible to use the model and the data? how exactly can we determine whether a model is a good and robust model? So here's my thought on this. If the model fits the data, then as you add more data, then the parameters should converge to a final solution. So let's look at this table. We start with 5 data points and we're adding a data point until all the data is sampled. The model is then applied to each data set. So with this fit, let's look at the results. L is the parameter that determines the maximum count of the death rate. And is it possible that it's converging at the very end as more data accumulates? For most of the data accumulation, it seems to be increasing, suggesting that the early data did not have much value in predicting the end result. And would this make for model error? Could the one bad data point be influencing the model? In my opinion, it somewhat does. We have this point here, this one higher point, and what follows also seems to be a little bit elevated. Everything that follows seems to be a little bit higher. So this is definitely not good and is something that should be improved when these statistics are taken in future cases. The growth rate parameter. It does seem to be converging and does not seem to be much affected by the bad data point. So when we look at this, we see a little bit of a convergence process going on here. So I think the data rate, the growth rate parameter is something that I think we can trust. And the peak epidemic parameter seems to be increasing as data accumulates and it's further disturbed by the bad data point. This would seem to be a model problem, as there is no evidence that the parameter is converging as the data increases. Right? We see again a jump here and then a somewhat elevated level of the next 4 or 5 points. But still, none of this changes the fact that the model is basically good. We are near the point of maximum decline of epidemic growth. So the L parameter and X0 parameter should still start to converge quickly if the model is good despite this bad data point. Again, we see we are having a red point here, the last data point that is at the minimum of the first derivative. Okay, this brings me at the end of today's session. I hope you had fun as much as I had. Hope I see you again on the next session. Thank you. Bye bye.